In Lesson 1.1, we're going to be working on finding patterns and expressions, and the objective of this lesson is to be able to identify and describe patterns that we see. So let's look at a geometric example. We want to determine the pattern for the shapes drawn below, and then we're supposed to draw the next pattern. So let's look at what we observe in the picture. Notice that we have a shape inside of a shape, and in the outside shape, we alternate between a rectangle and a circle. So we automatically know that our next shape needs to be a circle for the outer shape. Now, on the inside shape, notice that we are alternating also rectangles and circles, but we're always the opposite of what the outside shape is. So we also know that now we have a rectangle, or in this case maybe a square, inside. Now the next thing we need to do is look at the shading. Well, first thing you'll notice is that they are shaded opposite. So in this first example, the outside shape is plain and the inside shape is shaded. Then on the next example, we have the outside shape shaded and the inside shape is plain. So we just have to figure out how that shading is occurring. So notice what's happening there. We start with, and I'm just going to look at the outside shape and see what's happening. And we notice that the outside shape is plain, then shaded, shaded, plain, plain. So we would expect that the next one would be shaded. So then we want to shade our outside shape and keep our inside shape plain. So that would be the pattern that we're looking for. Now that actually should have been a fairly simple pattern to find, and what we're going to be doing now is looking at solving some problems that involve some numbers and looking for patterns in the numbers. So before we look at more examples, let's go ahead and look at some terminology that we're going to use throughout this course. So one of the things we'll talk about extensively is variables. So a variable is a symbol. Usually we're going to use letters. Sometimes that will be from our alphabet, sometimes maybe even the Greek alphabet. But it's a symbol that represents some unknown quantity or number. So I'm going to just put it represents an unknown quantity. Now the next thing we're going to have is a numerical expression. A numerical expression is some statement. We usually are talking about a mathematical statement. So it's a statement that has only numbers and operations. So a numerical expression might be something like 3 plus 5, or 2 times 7 divided by 7. Now an algebraic expression is very similar to that. It's also a statement, but this time it has at least one variable . And it could have constants or numbers, it doesn't have to, and operations. All right, so it might be something like 2x plus 4, or 3x minus 5y. Now we're going to look at another example, and this time we're going to try to complete a table to come up with some pattern that may lead us to some kind of an expression that will allow us to determine what's going to happen in any figure number without actually having to do the counting. So let's look at what we have here. We have some shapes drawn here. We are going to look for a pattern that relates the number of the shape to the number of the squares in the picture. So if we look at our first figure number, we'll notice that there is, and I'm going to go ahead and fill out the output, 2 squares in that. If I go to my second one, I notice there's 4 squares. My third one, there's 6. And my fourth one, there's 8. Now I'm going to go ahead and try to come up with some process that will allow me to look at the figure number and come up with the number of squares. Well, if I notice, what I'm going to do is take my figure number and multiply it by 2 and that gives me my output. In the second example, if I take my figure number 2 and multiply it by 2, I get 4. If I take my third figure number and multiply it by 2, I get 6. And that also works for my fourth one. So using that pattern, I should now know the seventh one would be just 7 times 2, which would be 14. And now what we're going to do is come up with what we call an nth term expression. So I'm looking for what happens on the nth figure number. So looking at my process column, I'm noticing that if I take whatever my figure number is and multiply it by 2, that's giving me my output. Well, n times 2 can also be written as 2n. In our last example, we're going to look at a graph. We're going to fill out a table and then come up with a relationship between the number of toppings on a hamburger and the cost of the hamburger. So let's look at just what we have in our table. If we have 0 toppings, you can see that there is a point there at 4. So my cost would be $4. For 1 topping, well, I'm between 4 and 6, so we're going to call that 5. For 3 toppings, and notice I'm not counting sequentially here, it was 7. For 6 toppings, it was 10. And we don't have 10 in our table, so we're going to leave that blank and we're going to look for our pattern and then come back and fill that in. So let's look at what's happening. For 0 toppings, we went to $4. 1 topping went to 5. 3 toppings went to 7. 6 toppings went to 10. So what I can see is that if I take the number of toppings that I have and I add 4 to it, that's giving me my cost. So we now know, if that's my formula, that if there are 10 toppings, add $4, we get that the total cost will be $14. So if there are n toppings, n plus 4 would be just n plus 4. That doesn't simplify. That would be my formula to find the cost. So now we have found our relationship. Let's write that now in an equation. Our cost is equal to the number of toppings plus 4. Now we're going to use that to see how many toppings are there with a hamburger that cost $18. So I know that the cost is $18. And I want to know how many toppings, what would n have to be, so that the output would be 18. Well, we know that that means there would have to be 14 toppings on that hamburger to get a cost of $18.